So today, 2 quick proofs and that's it. We're proving the fundamental theorem of calculus, which is basically proving that the integral of a derivative gets you back where you started. So have a function, take its derivative, and then integrate it, and you're back where you started. That's essentially what we're proving. Books. Open up my book. Oh shoot, what page? 6.5. Are you seniors the ones doing the breakfast for the past seniors?
Yes.
Oh, okay. I wondered.
You don't do that?
I wasn't going to, but my brother Ham made it pretty clear that he expects the teachers there, so kind of took the choice out of it. So now I am going. Yeah, I'm not big on fancy meals. There's just no tail there. Makes no sense to me.
Doesn't taste good.
It tastes good, but it's like so much effort for something that just tastes good. It's just not worth it.
Yeah, but we're putting in the effort. You're just gonna eat the food.
No, I'm talking about the effort of me going and putting myself somewhere
So it's effort to
For-
go socialize?
an entire hour for a meal.
Oh,
Like
for
I hate
a
when a
while.
meal is an event.
So you hate like going to
Why?
restaurants?
I hate going to restaurants. It's like I go in there and I just gotta sit there and wait for them to prepare my food. It's like I could have easily whipped myself up something that I'm just as happy with, and it only takes me 10 minutes.
Do you guys
And I can do
gonna
other
bring
things.
like a +1?
Huh?
Do you guys gonna like bring a +1?
No, they say that there's gonna be like 200 people there, but
Teachers,
They don't get a bring.
it's kids, the parents, and teachers, and no one else.
I don't know how they get to 200. I thought that the seniors could only bring one.
They don't care.
No.
It's two.
They get bring two?
Yeah.
Okay,
So
maybe I
that's
misunderstood.
like,
I
it's
mean,
like
even
30
two
people,
is
and
limiting
then
it.
2 parents.
So that's 90.
And staff is probably another 30.
Yeah, so that's 120.
I don't know.
I don't know how it got to 200.
I remember the guest list being like 150.
Yeah, we
Oh,
were rounding
150.
it to 150, and then they probably rounded 150 to 200.
Oh,
That
okay.
But 150 is rounded, so.
Oh, okay. That makes more sense. Anyways, we can talk about that later. Let's quickly prove this stuff while we're recording. First though, lemma. I don't even know how much we need to write this whole thing out because it's only got a couple lines. But the idea is that if we have a number, so let's start by writing out what the function is actually. May as well just write it out. So we'll just write it. So this is lemma 6.21. Suppose f from a, b to r. Quick reminder of what we did last time. You remember what we proved last week?
Continuity and
We proved that a continuous function on a closed-bounded interval is integrable, and furthermore, the value of the integral doesn't depend on the endpoints. So it only has to actually be continuous on the open interval a, b, not necessarily the endpoints. So that's what we did last time, and now this time essentially, let me write down the big idea of what we're going towards. We're going to be proving that the integral from a to b of f prime of x dx is equal to f of b minus f of a, where f prime is the derivative of big F. F prime of x is the derivative of f of x. So let's do a really quick concrete example to help us see this. So let's say I want the integral from 2 to 9 of x cubed dx. So I'm looking for the function whose derivative is x cubed. And it's like we're doing the reverse of the inverse of the power rule. You remember what the power rule is, right? It's if I have xn, I want to take its derivative. So if we do the derivative with respect to x of xn, then that's equal to n times x to the n minus 1, right? So now, undoing what we did here, notice that we multiplied by whatever the exponent was, and then subtracted 1. The inverse of that is going to be adding 1 to the exponent and then dividing by it. So now if I want to get from here to here, what do? I need to add 1 to the exponent and then divide by it. And that does it, and I'll get back to x to the n. So the integral of x to the n is going to be equal to, dx, is going to be equal to x to the n plus 1 divided by n plus 1. It's going to do the opposite of what this does.
And your n plus 1.
N plus 1, whatever the exponent ends up at. It's just that we have n plus 1s here where we had n's here. So notice if I do this and I apply this operation to it, I'll get this. So let's add 1 to the exponent. N minus 1 plus 1 is n. So now n plus 1, the n's are different here. Maybe put n to help get rid of some of the confusion. Let's just go through it with an actual function. So let's start out with a function. Let's do x to the 5. What's its derivative? The derivative of x to the 5 with respect to x is equal to, pull down the 5, we get 5 times x to the 4 now, right? So now let's look at the integral of 5x to the 4 dx. This is equal to, add 1 to the exponent, so that's going to be x to the 5, and then divided by it. So 5 divided by 5 cancels out. So this would have been 5 times x to the 5 divided by 5 is equal to x to the 5 when we apply this operation. The constants are going to pull out the same way that they always have. Remember that this and this, these are just limits. A constant times something that you're taking the limit of, you can always pull the constant out.
So, how does that, my confusion is, on an integral, you have to have it on an interval from a to b?
Oh, yeah, so how can I quickly say that without just continuing? Yeah, so if we do an indefinite integral like this, it's actually going to be plus a constant, c, where c is any number. Because now this, when you take the derivative of this, you'll always get this. You can add any constant, it doesn't change the derivative. So that's how you would handle that. It's an indefinite integral, meaning we don't have its exact value, but it's of the form x to the 5 plus some constant. We don't know anything about what that constant is. Putting bounds on here determines what your constant is.
Okay. Are we going to learn, like, generally use solve integrals in a regular calculus class?
This is it. We'd teach you this, and we'd start going over our derivatives and doing the anti-version of that derivative.
Okay.
So you'd say, when we took the derivative of this, we got this, so when we're trying to undo it, that's like this.
It's the inverse.
Yep. And then there's general methods of integration that we won't be covering in this class, like integration by parts, fraction decomposition. There's methods for how to integrate different types of functions, but integrating is much more difficult than differentiating. And so there's a bunch of methods for trying to figure out how to do it. Because there's some things that we just, simple looking things that we just don't know how to handle with basic math notation. Anyways, that's what we're working our way up towards. The idea that the integral and the derivative are somehow inverses of each other. So back to this lemma. suppose that this function f from AB to R is integrable. And there's an A. And that big A in R has the property that for every partition on AB, the lower Darboux-sum with that partition is less than or equal to A is less than or equal to the upper Darboux-sum on that partition. Then the integral of f. Then the integral from A to B of f is equal to A. Okay, here's what the limit is. It's more work to write up what it is than it is to actually prove it.
Haven't we already proved something like that? Isn't that the definition of the integral?
Basically, right? So we're almost there. All you have to do is keep in mind from last week we know. So first off, we know that this thing is integrable, right? So we know that the integral exists, and the integral is going to be
Limit of the upper and lower Darboux-sums.
yeah. So since this is an upper bound, then it's going to be greater than, well, not the upper and lower Darboux-sums, but the upper and lower integral.
Right.
Right. Where what's the lower integral? It's the infimum of lower bounds, and then the upper integral is a supremum of upper Darboux-sums. Right? Supremum, least upper bound.
Okay.
Oh, but I said those backwards, didn't I?
Yeah.
Supremum here, least upper bound, infimum here. Yes, thank you. So, we're going to notice that this is an upper bound of this, right? A is an upper bound of this, and then the lower integral is a supremum, so it's the least upper bound. So we get 1, observe that the lower integral from A to B of f is less than or equal to A. A is an upper bound for the lower Darboux-sums. Sorry, this is lower integral. This is the least upper bound. And then similar logic for it's also between from A to B, the upper integral in f. Because what is this? This is the least upper bound, or the greatest lower bound, sorry. This is the greatest lower bound. This is a lower bound.
That's the greatest lower bound?
Yes, this is the greatest lower bound for upper Darboux-sums. Upper Darboux-sums, as they get better and better, they get smaller and smaller.
Yeah, I see what you're saying.
Okay, so we know that A sandwiched between those. And since f is integrable, that gives us that the integral from A to B, the lower integral is equal to the integral is equal to the upper integral, right? Which gives us that the integral is equal to A. So that one's pretty straightforward. It's just a mouthful, right? You know what you're starting with. Make sense? Okay, so now we're ready to prove the actual part of the section, which is the fundamental theorem of calculus. The idea that an integral gives you an that you can express an integral of a function in terms of its antiderivative. So that's the terminology we use, antiderivative. What's the antiderivative of this? X to the 5. The antiderivative of that is x to the 6 over 6. That's its antiderivative. So if this is f prime of x is equal to that, then f of x is equal to that plus some constant. Because when you take the derivative of this, you get this. Make sense? And that's how you find the antiderivative. You're just looking for the function such that when you take its derivative, you get this. So this is an antiderivative of this function. Okay. So let's actually write down all the terminology. Write out the whole thing that we're trying to prove. So, Theorem 6.22. Let f be a function from a, b to r such that f is continuous on the entire closed interval ab and differentiable on the open interval ab. Moreover, suppose that its derivative f prime, oh, we did a capital F, let me follow this convention. Capital F, capital F.
Is there a reason that you're capital instead of the other?
When I think that they typically use capital F to represent the antiderivative of some function as a general rule. So that when you see a capital F, you know, oh, this is supposed to be thought about in terms of an antiderivative of some function. So just a way to help keep it in your mind, we're talking about an antiderivative function. I think even with your standard calculus textbooks, when they introduce this theorem, they use the capital F the same way. F prime, the derivative from AB to R is both bounded and continuous. Both continuous and bounded. Then the integral from a to b of f prime of x dx is equal to f of b minus f of a. Okay.
You said this was the fundamental theorem of calculus?
Yes.
I thought that, well, you said that it was proving that if you take a derivative of a function and then take the integral of that derivative, then you get back to the function.
Yeah, I said that bad. It's called the first fundamental theorem of calculus. It's the idea that integrating a derivative gives you an antiderivative. So we're integrating derivatives. And then the second one is going to be taking the derivative of integrals. So this one's integrating derivatives, the next one's going to be differentiating integrals. And then those together show you how you can go back and forth. So if you take the integral of a derivative of a function, you express it in terms of the function.
Right?
I don't know. I feel like I'm saying it weird, but this exact thing.
Can we have like is there a way to represent it visually on a graph?
Is there a way to an intuitive way to represent it? I think that the most intuitive way to get a feel for this is thinking about positions and velocities, because it's fairly intuitive that a velocity is a change in position, right?
Okay.
So, does that appeal to your intuition? You think about a derivative as how a function changes.
Yeah.
Right? Okay, so that's exactly what velocity is. Velocity is how your position changes. Right now I have no velocity. If we call that way positive, now I have a velocity of 1 meter per second. My position is changing.
Okay.
So, if we were to plot my velocity with time, let's say that my velocity, let's just keep it simple, and let's say I have a constant velocity. So I'm just walking with a constant velocity of 1 meter per second. So my velocity after 1 second is, at 0 seconds, is 1. My velocity after 1 second is 1. My velocity after 2 seconds is still 1. My velocity after 3 seconds, let's not do 1, so they come out a little different. Let's pick a velocity slightly higher. I didn't need to erase my picture, I'll still just do a constant velocity. But we'll do a constant velocity, we'll say I'm moving at 2 meters per second. So here's 2, and here's my velocity. Just constantly running at 2 meters per second. Good? So now, velocities change in position. Maybe to help see the back and forth, I'll also plot my position. So there's my velocity function, my position function. My position function is going to start out 0, and then after 1 second I'll be 2 meters, after 2 seconds I'll be 4 meters, after 3 seconds I'll be 6 meters, etc. Right? So my position function, let's see, try and keep this is meters per second, and then this is time. Over here we have, here's my position, and this is time. And over here it's going to look something like this. I'm not going to draw it to scale, so we'll just draw it slanted like that. So my x-axis is more squished than my y-axis. So after 1 second, I'm over here at 2. After 2 seconds, I'm over here at 4 meters, right? So we'll just look at the first 2 seconds. So after 2 seconds, I've gone 4 meters. Good? And over here, after 1 second, I'm going 2 meters per second. And after 2 seconds, I'm going 2 meters per second. So here's my velocity with respect to time. Here's my position with respect to time. Now, what is the equation of this line right here? The equation of this line is just f of x is equal to 2x. 2t, sorry, f of t. Because we're doing it with respect to time, right? And over here, what's the equation of this function? The equation of this function is just f of t is equal to 2. Good so far? Okay, so notice that when I take the derivative of this function, I get this function. This function is the derivative of this function. This is my position function, this is my velocity function. What's the derivative of 2t? It's just 2. So let's call this one big F of t, and we'll call this one f prime of t. Good? Now, what we're saying is, I can integrate over here to figure out my displacement. So, if I want the integral from 0 to 2, the way that, what this would represent if we ask it over here, the integral of f prime of t dt, this is asking, how much does my position change from time 0 to time 2? Let's pick a different, let's go 1 to 3 so that we can see the A and the B here. So that will help. So let's just ask a question now. Just come and look over here to begin with. How much does my position change in how much does my position change from time equal 1 to time equal 3?
4.
It changes by 4. How do you figure that out? You do f at 3 minus f at 1. Right? What we're saying is, yeah, you could look at this function and figure it out that way. Or you could look at the area under our velocity function and calculate that way. So if you look at this area here, this will also give you the same thing. That will give you how much distance you've covered. If you plot your velocity function, the area under it gives you the distance that you've covered.
Okay.
So we're saying that the integral from f prime of t, the integral of this function is obviously just 2 now. So let's write it out again. This is the same thing as the integral from 1 to 3 of just 2 dt, right? I just plugged in the function. Now, we need to find the antiderivative of 2. What is the number? What's the function such that when you take its derivative, you get 2? 2t. Take the derivative of this, you get 2. Right? So this is the antiderivative of 2. The derivative of 2t is 2. So the antiderivative of 2 is 2t.
So the integral of the derivative is the antiderivative.
Yes. Yes. The integral of the derivative function on some bound, a to b, in this case 1 to 3, is going to equal the antiderivative evaluated from 1 to 3. That's what we use to say evaluate from 1 to 3. What we mean is plug this in and subtract what you get when you plug this in. So that's the same thing as 2 times 3 minus 2 times 1, which is the same thing as f of 3 minus f of 1. It's the exact same thing that we did over here in trying to figure out how far it went. That's what we're doing. We're basically proving that you can do this as a general rule, and not just in this one special case. Anything weird there?
It's just going to take some getting used to calling it an antiderivative. It's a reduced function. That's like,
Yeah,
this
just
is the way I'm thinking about it up until this point is just, oh, that's the function we're starting with. No, just threw it off for a second.
yeah, it's just inverse the same way. How do you undo multiplication? Division. How do you undo division? Multiplication. How do you undo a derivative? Antiderivative. You start with this, take its derivative, you get this. Take its antiderivative, you get this. Undoes the derivative.
So the integral is the antiderivative.
The integral can be expressed in terms of antiderivatives. When it's an integral on some bound. If it's an indefinite integral, then yeah, it just is an antiderivative plus a constant. Because there isn't just one antiderivative. There's infinite many. Because the antiderivative of 2 is actually 2t plus any constant here. Plus any constant you want there. And when you take its derivative, you get this. But here is an antiderivative. And so you just need an antiderivative for this to work. You don't need the antiderivative. Because we could have just as easily called this function over here 2t plus 9. Imagine that we graph that thing. And we could do this and we'd still get the exact same thing. That wouldn't change anything in the math. Because you plus 9 on one side and subtract 9 on the other side, the 9s go out.
Right.
So if we would have left this just plus c, we still would have been fine. Because then when we evaluate it here, it would be 2 times 3 plus c, and then we would have had minus c over here, which is exactly what that is. It doesn't change the answer. Make sense? Okay, so there's some intuition. Alright, so now let's prove this. So we're integrating this thing. We know that this thing is both continuous and bounded on this interval. So it's going to be integrable on this interval, since extending it to the endpoints, the interval doesn't depend on the endpoints. That's probably where it's going to start. The function that is continuous and bounded, thus by theorem 6.19, is integrable on AB. So, 1. Since f prime is continuous and bounded on AB, it is integrable on the closed interval AB. And that's theorem 6.19 that we did last week. The idea that the integral doesn't depend on the value of the endpoints. Make sense? So now, using our preceding lemma, let's see. By the preceding lemma, in order to verify this integral, it suffices just to verify we'll just say it remains to show, and then just write this inequality up here. Remains to show that for any partition P, that the upper Darboux-sum on f prime, no, start with the lower, our inequality. We're going to reference our previous lemma here. Our previous lemma is that if A has a property that's always sandwiched between the upper and lower Darboux-sums on something that's integrable, then it is the value of the integral. So we're going to say our lower Darboux-sum on f prime with our partition P is less than or equal to f, not f prime, but f of B minus f of A, which is less than or equal to the upper Darboux-sum on f prime with that same P. So if we can show that this is the case, then we're done. You follow that? See how that's just using the preceding lemma? This is our number A from the preceding lemma. We proved on the preceding lemma that if there is some number that is always sandwiched between the upper and lower Darboux-sums on something that's integrable, it is the value of the integral. And pay attention to the fact that we have f prime there and f there. Okay, so that's what we got to do. So let's just pick some partition. Let P be a partition. Then, well, we're going to need a sequence of partitions where the gap goes to 0. Let's see how it says that. I don't know, because that's for any partition. So if we just do it for any partition, we're fine. But let's name it. Let P equal to x naught, x1, comma, dot, 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 comma, xn be a partition. Okay. Then, we know that our, what's the right way to do this? Maybe a picture really quick to help with our intuition what we're going to do here. So we've got some function defined on the closed interval AB. What we're going to do is we're going to look at a particular interval and reason about just a particular interval. So this is x sub I minus 1, make it bigger so that those aren't close together, to x sub I. We're going to pick a particular interval and we're going to apply the mean value theorem to this particular interval. Way back to the mean value theorem. Do you remember the mean value theorem? What does it say?
says that if it, essentially, the way I think about it is if it's increasing and then it's decreasing at some point, the derivative is 0.
Not 0. It's going to be the average rate of change.
Yeah.
So take your average rate of change over this interval, which is going to be the slope of that line. We're saying that there's going to be some point in the function in between here, such that the value there is, the derivative there is equal to that.
Yeah.
So, the mean value theorem says that there exists, we'll call it point C sub I in x sub I minus 1 to x sub I, such that, what is this mean value here? It's going to be rise over run, right? Such that, which function are we going to be talking about right here? This function right here, f. So if this is our function f, well, we'll ignore that for a second. We'll just call it little f. We'll think of this as a side picture for a second. So we've got function little f here. We're saying that there exists some point here, in here, we'll call it C sub I, such that f of b minus f of a, oops, not f of b, f of x sub I minus f of x sub I minus 1 all over x sub I minus x sub I minus 1 is equal to f prime at C sub I. This is the average slope on this interval, rise over run. And we're saying that there exists some point in there such that the derivative at that point gives us the average slope. Make sense? Now we're going to rework this a little bit. We're going to do this is equal to this. We're going to move that over there basically. Now let me re-express this in terms of big F's now, because then I think you'll see the connection. So we're going to show that f of x sub I minus f of x sub I minus 1, as a subscript, minus 1, is equal to f prime at C sub I times x sub I minus x sub I minus 1.
Is that supposed to be little f or big F?
Sorry, big F prime. Yep, these are all big F's now. You see that? And so, since this is true, we're going to sandwich this value then between little m sub I times x sub I minus x sub I minus 1 is going to be less than or equal to f of x sub I minus f of x sub I minus 1 is less than or equal to big M sub I times x sub I minus x sub I minus 1. Where the big M sub I and the little m sub I are the max values achieved by the derivative function, not the actual function. So notice, if we're talking about if m sub I is the smallest value the derivative function reaches on this interval, and big M sub I is the biggest value the derivative function reaches on this interval, then the derivative function at a point on that interval, this is going to be greater than or equal to little m sub I, and this is going to be greater than or equal to big M sub I. And since this is equal to this, and since this, if we put this here, it's obviously sandwiched between these two, then this is sandwiched between these two, and we're doing that on every interval. Maybe if I make some things more explicit over here, we'll be fine. Let that be a partition, comma, and let x sub I to x sub I minus 1 be any partition interval. So just pick some partition interval. And maybe we'll redefine little m sub I and big M sub I to help just cement things in. Let little m sub I equal, let's see, little m is going to be the least upper bound, so it's the supremum. So let this be the supremum of f prime of x, where x is in x of I minus 1 to x of I. And let big M sub I be the infimum. Infimum of all f prime of x values on the closed interval x in x of I minus 1, x of I. Okay, so little m sub I and big M sub I make sense so far, right? We got f prime is a function on some interval. It achieves some minimum value on that interval, and it achieves some maximum value on that interval. Because we know that f prime is both continuous and bounded.
How's the supremum the minimum value it achieves?
Did you,
Did you switch them, or am I just thinking that wrong?
The supremum is the least upper bound, right?
Yeah.
Did I do that again? Yes, you're right. I can't believe I keep doing this. Infimum. The greatest lower bound of all those. So this is a lower bound. This is an upper bound. Thank you.
So if your function over there was f prime x,
This function was f.
right, but if it was f prime, then it would be the 2 points that you have marked out on it. For m sub I and
No, little m sub I would be somewhere like right there. Big M sub I would be somewhere up here.
Oh, right.
The least value and the greatest value that they achieve on that interval. Or the reason that we're doing infimum and supremum instead of I think I need to make those open intervals because a function's not necessarily using the endpoints. Min and max. Oh, we wouldn't know that it achieves a min and max anyways. Would we? A continuous function on a closed bounded interval achieves a minimum and a maximum. But we're using infimum and supremum. So by assumption, the function that is continuous and closed on the interval and differentiable on the open interval by the mean value theorem. Yeah, I know that. Since point Ci belongs to the interval, yeah. Well, I don't want to confuse you by, so we'll come back and talk about why we're doing this instead of max and min in a sec. But let's continue with our train of thought first. Okay, so let little m sub I be the minimum value it achieves and big M sub I be the max value it achieves. Okay, so now we know, maybe just make this point explicit. Well, no, I don't think we need to. Okay, so that's just defining those things. Now we're going to use the mean value theorem. So, mean value theorem. Since f prime on x sub I minus 1 to x sub I, from that to R, so when we restrict f prime to just this one partition interval, it is continuous. And bounded. Because it could be the first or last interval, which wouldn't necessarily be bounded on the closed interval. It's only on the open. So, but we know it's continuous and bounded. So, since f prime is continuous and bounded, then by the mean value theorem, there exists some point Ci in x sub I minus 1 to x sub I such that exactly what we wrote over there, except for I'm going to skip down to writing it this way instead of writing it that way. Oops. No, we use mean value theorem on f, not on f prime. Sorry. Okay. So let's see. We still know that this is continuous on that, on the closed interval. Since it's continuous, it is also bounded. Okay, but we didn't really specify that now. Okay, that clears that up. So since f, big F, is continuous and bounded, then we can apply the mean value theorem to it, right? Exact same picture we had over here. So then, by the mean value theorem, there exists at some point C naught such that the derivative at that point is equal to, the slope at that point is equal to the average slope across the interval. Maybe we'll just write it all the way out like this to make sure I know. Just make sure anything. So that's just using the mean value theorem, right? Average slope across the interval, there's going to be a point where the slope at that point is the average slope. Mean value theorem. Big F is a continuous bounded function. Big F on this closed interval right here is a continuous bounded function. So there has to be some point in that interval such that the slope at that point is equal to the average slope. This is just rise over run. y1 minus y0 over x1 minus x0. Okay, rewriting this now, this is the exact same thing as f of x of I minus f of x of I minus 1 is equal to f prime at c sub I times x of I minus x sub I minus 1. Let me do rounded parentheses so I don't accidentally think about this. This is a close interval. So that's just a number. Right? Simple algebra there. Now, let's mention our little m sub I and big M sub I. Observe that little m sub I less than or equal to c sub I is less than or equal to big M sub I for every partition interval. Right? We define this c sub I for every partition interval that we pick, and this is always going to be the case, this inequality. F at c sub I. Sorry. F at c sub I. F prime, because this was defined on F prime. The value at that point. The value anywhere on the function is always sandwiched between these two, as long as that value came from the interval.
Why is it f prime instead of f?
Right here. Little m sub I is equal to the infimum of f prime on that interval. Greatest lower bound. But it is a lower bound. So this is the lower bound for this, always and forever. And this is an upper bound for this, always and forever. By definition of little m sub I and big M sub I. Right? Okay, so now we can tie it all together with the algebra showing the inequality that we're after. Then, lower Darboux-sum on f prime with p is going to equal the sum from I equals 1 to n of little m sub I. Am I skipping a step that's not going to work? Let me come back and write one more inequality here, and then we'll go where I'm going. Then, little m sub I times x sub I minus x sub I minus 1 is less than or equal to plug both these in to help make it very clear. C sub I times x sub I minus x sub I minus 1, which is the same thing now as f of x sub I minus f, notice we switch from f prime to f, at x sub I minus 1, which is less than or equal to big M sub I times x sub I minus x sub I minus 1. That right there is the heart of the whole proof. You see that? I know that this value is less than or equal to this value is less than or equal to this value. That's exactly what I have written right here. Okay, here's where was that. Take this inequality, and now I'm going to multiply this by x sub I minus x sub I minus 1. Same with this, same with this. So multiply that to this term, multiply that to this term, which happens to be the same thing as this. And now multiply that to this term.
How do we know those are equal?
Intermediate value theorem, or mean value theorem, by definition of C sub I. C sub I is a magical point that makes this equation true. Good? Because, yeah, if you can understand this line, we're basically done. So let's make sure we understand that line.
For some reason, I feel like the line I'm struggling with most is still line 5, even though we've gone over it multiple times.
Line 5. Okay, so F, here's big F. Of x, yes. This function is a closed-bounded continuous function. It's defined on a closed-bounded interval, it's continuous. So what does that mean? It means the mean value theorem applies. It means that if my function, however my function changes from some point to some point, pick 2 points on the function, doesn't matter where. What's the average change from this point to this point? It's just the slope between those 2 points. The slope of the line that goes through those 2 points. That's going to be its average change. Is that the part that's not intuitive?
Okay, that makes sense.
So that's its average change. The mean value theorem says somewhere in between these 2 points, there's going to be a point on the function such that the instantaneous change, or the derivative at that point, is equal to the average change over the whole interval. Or in other words, there's going to be a point on the line somewhere such that the tangent line has the same slope as this line. So if we take the tangent line here, the tangent line at that point has the same slope as this slope. So the slope at C sub I is equal to the average slope across the whole interval. Here's just algebra. Multiplying top and bottom by same.
Oh, okay.
Okay. So now we know that we can go from this to this. So it's this value that we sandwich, and in that way we sandwich this value. How do we sandwich this value? We know that this right here is between little m sub I and big M sub I. So this whole value is sandwiched between this whole value and this whole value. That make sense? Yeah. Okay. So now that we have all those values sandwiched, sum up those values. So then, the lower Darboux-sum, because that's exactly what this gives me when I sum it up all the way, is the lower Darboux-sum. If I sum this value up on every interval, that is my lower Darboux-sum. So the lower Darboux-sum on f prime with p is less than or equal to this, but it's also less than or equal to this, summed up on every interval. So maybe before we plug that in, we'll just write it this way, so that we don't do too much in one go. The sum from I equals 1 to n of f of x sub I minus f of x sub I minus 1. We're summing that whole thing. Right? Which we know is less than or equal to this, the sum of all these, which is the upper Darboux-sum. Right?
Yes.
Because now we're just summing up all n of these across all the partitions. There's m partitions. This was for a particular partition. Since it's true for each individual partition, it's also going to be true for their sums. So we're summing up all n of these, that's that. We're summing up all n of these, that's that. We're summing up all n of these, that's that. Okay, so then the last thing, which remains for you to grasp, is that this right here is f of b minus f of a.
Yeah.
If you sum up the difference of height of a function across each of the intervals, your total sum is going to be your total difference. Does that make intuitive sense, or do we need to like draw a picture to see that? No, it doesn't make intuitive sense? So,
We did a picture of it before.
yeah, we've done a couple pictures of it before. With the rectangles.
Mm-hmm.
So, I'm trying to think about the most intuitive way to say this. Because there's a discrete number of changes to those. So let me just draw a clean picture, and let's draw it up there and see it. So we'll draw this. We'll just make a small partition that doesn't have very many points in it, just to keep it simple. And then we'll make our function something that's just always increasing, so that the picture stays clean. So, from here to here, this height, this is f at, so this we'll call the point x0, x1, x2, and x3. So, this height, if we add up the height of this part, and then the change from here to here, gives us the height of this part, and then the change from here to here gives us the height of this part. If we add up all these changes, that's the same thing as adding up the change from where we started to where we ended.
Mm-hmm.
So that makes intuitive sense, because this is also A and this is also B. So we're saying f of B minus f of A, well let's just plug it in, we'll see that same thing. So we have, what's the change here? This is f at x1 minus f at x0, plus, what's the change here? This is f at x2 minus f at x1, f at x2 minus f at x1, plus, what's the change here? This is f at x3 minus f at x2. Now notice that everything except for f of x0 and f of x1, or f of x3, which is the same thing as f of a, x0 and a are the same thing, and x3 is the same thing as f of b. Everything else is getting canceled. That's going to be negative. So x1 cancels out with x1, x2 cancels out with x2, and now we have a negative f of a plus f of b, or f of b minus f of a. So since we showed that this value is sandwiched between these two things, then by the preceding theorem, or the preceding lemma, it is the integral. So that gives me that. The integral from a to b of f prime of x dx is equal to f of b minus f of a. And that's the whole section, just that one theorem, basically. I recommend just reading what the author has there. He makes it pretty clear. It's not that hard. I don't think it's that hard. Maybe I should say that. As long as you remember the mean value theorem, I think that this proof is pretty straightforward. You have any questions on it? Trying to come up with a question?
I don't think I have any questions, like, it all kind of makes sense, but it's just not solid.
Alright, well. Read the author's proof, I guess. See another way of saying the same thing. And then this just tells us, okay, so now you know how to integrate some things now. If it's something that, if you're looking at a function, you can figure out what it's the derivative of, you can now calculate its integral. And that's it.